Okay, can you hear me? Okay, so now I start recording. Okay, welcome to this new lecture. I will start sharing the screen. Okay, so now you should see the slides. Okay, so now. Okay, so in the previous lectures, we have seen theoretical aspects of machine learning. We have talked about model selection. We have seen the decomposition of bias and variance. And we have also talked about how we can try to model the complexity of an hypothesis space, like using the VC dimension, and use this to bound the relationship between the train error and the true error or the prediction error. So we have established these theoretical tools of machine learning that now can help us in understanding more complex techniques with respect to the linear method that we have seen in the first part of the course. So today we will see a different kind of methods with respect to the previous one, that are the kernel method. Kernel method is a family of machine learning techniques that is very interesting and that has aspects that is worth studying. So this is the plan. So today we will focus on the definition of what is a kernel method. We will talk about the dual representation and how to build kernels. And then probably next time we will see what are some examples of kernel methods like radial basis function or Gaussian processes. And then we will see also the support vector machines, that is another kind of kernel method. So let's start introducing what is a kernel method. First of all, kernel methods are non-parametric. At the very beginning of the course, we have distinguished between parametric method and a non-parametric method. When we talk about parametric method, like for instance linear regression or logistic regression or neural networks, actually what you do is to define an hypothesis space where each single hypothesis is identified by the values of the parameters of the model. So you fix the parameter space, so the parameters that your model has, and then you can change the value of the parameters in order to define a new hypothesis. These are parametric methods. When we talk about a non-parametric method, in non-parametric method, actually, you have no explicitly the parameters of your model, but actually the parameters are somehow implicit, and actually they vary according to the size of the training set. For instance, this is the case when you have a memory-based method, like a kernel method. Memory-based methods are methods that produce the prediction for the given input by looking at the data that you have in the training set. So the main difference is the following. When you have a parametric method, you get the training set, you train the model by identifying the best parameters of your model, and then for doing the prediction, you need only what? The input data for which you have to do the prediction, and the value of the parameters. The training dataset, once you have trained the model, becomes useless. So you can forget it, because all that was interesting was learned inside the parameter of the model. So with parametric model, once you have trained the model, you can discard the training set and doing the prediction only with your model. This is not the same for memory-based method like in kernel methods, because when you have a memory-based method, each time in which you have to make a prediction, you need to go back to the training set, and so use the memory of your data, and look for the values of the data in the training set. because the model is implicitly encoded in the training data that cannot be discarded. I make you an example of this. Suppose that you use the k-nearest neighbor approach. The k-nearest neighbor approach is the method that takes the k examples in the dataset that are closest to the point where you want to do the prediction. So you get the input data where you have to do the prediction, you go back in the training set, you search for all the samples in the training set, and you select the k nearest example to the one where you have to do the prediction. And then you do averaging if you have to do regression, or majority voting if you have to do classification. But as you can imagine, with k-nearest neighbors, you can erase the dataset. You need the dataset. You have no explicit parameters of the model that encode your knowledge, because your knowledge is encoded in the training set. And so the training set needs to be preserved, because this is how you do the prediction. And as you can notice, when you use a memory-based approach like k-nearest neighbor, the training time is very small, or it doesn't exist. Because actually, for k-nearest neighbor, what is the training time? You have no training time. The training time is only storing the data. Once you have the data, you have nothing to do. All the time of the algorithm is spent when you do the prediction. Because when you do the prediction, you have to go through the dataset and compute the distances of all the samples in the training set with respect to the point where you have to make the prediction, and then doing averages. So memory-based approaches are very fast in training, because usually they have small training time or even zero training time, but can be quite expensive when they do when they are asked for a prediction, because at that time they have to do the operations. So this is quite important when you have to decide which technique to use, because of course, if your main concern is to be real time in doing the prediction, parametric methods are better, because maybe you take a lot of time for training them, but once you have trained them, they encode everything in maybe in a few parameters that can be used for very quick predictions. On the other hand, if you have no real problem in time for the prediction, so you can take your time in doing the prediction, but you prefer to save time for training, because maybe you have a very large data set and maybe training a parametric model can take too much time, maybe it's better to use a kernel method or a memory-based method. Okay, so summarizing, so we have said that in a memory-based approach, actually in the prediction phase, we still use the training data. This is different from the parametric case. So as we have said, if you use this kind of approach, they are usually very fast to train, but they are slow in the prediction. And as we will see, we needed to define a metric. That was not necessary for the parametric case. What does this mean? For instance, if you want to use, again, I do the example of k-nearest neighbor. Even if k-nearest neighbor is not a kernel method, is a memory-based method, but is not a kernel method. But is useful to explain to you some characteristics of memory-based approaches. When you want to use a k-nearest neighbor, in order to define which are the k points that are closest to the query point, of course, you need to define the metric. So how you measure the distance between the points and the query point? You need to define the metric. And this is true for all the memory-based approaches, and so in particular is true also for kernel method. You need a way to measure the distance or the similarity between different points. So this is different from the case of parametric method, because when we use the linear regression or logistic regression, we were not asked for defining a distance between points. In the parametric case, what you are asked for, what you need to provide. Because as we have said, in machine learning, nothing is for free. You need to provide a loss function. This, as we will see, this is also true for memory-based methods. But in order to specify your hypothesis space, you have to provide also the optimization. This is true for all the supervised learning. So the loss function, the hypothesis space, if you want, the optimization method are common to all the supervised learning method. For what concerns the hypothesis space, as we will see here, you have to specify the metric. For memory-based, you have to specify the metric among points. While in parametric method, you have to specify the features. Yes, you can see as the number of parameters, but more than the number of parameters is the features that are associated to the parameters. Okay, so the important thing is that in parametric method you have to provide the features. So while in parametric you provide features, in memory-based method you do not provide actually the features, but you provide the distance between the samples. And as we will see, there is actually a strong duality between the features and how you measure the distance or the similarity among the samples, that is the metric. We will see that we can move in among these two modes, the parametric mode and the kernel mode word, by this duality of features versus similarity matrix. Let's see this concept. Okay, so we have seen this many times when we have talked about linear regression and linear classification. We have seen that actually if you want to capture nonlinear behavior in your target function, you can use what? You can use features. So you change the inputs by adding more features to your data set. These features are strange combination of the input variables that allow your linear method to represent a nonlinear combination. So we have seen many times this concept. So we have seen that you have a linear model. For instance, your linear model for regression in the first case and for classification in the second case on the right. So on the left, you have a regression problem where a linear model is not good. On the right, you have a classification problem where a linear model is not good. But we have seen that this problem can even be solved by linear method if you change the input representation by adding other features. So this is the way in which you solve the problem when you are in the parametric world. Kernel methods have a different way of solving the same problem. The good thing that we will see is that actually kernel methods are able to do the same thing that you do in the parametric method by adding many features in a very clever way, in a way that is very computationally efficient. And in particular, we will see that you can always map a parametric method with an arbitrary number of features to a kernel method that solves the same problem. What is the main difference? The difference is the following. When you are in the parametric world, for instance, linear regression, the computational complexity of learning the best parameter is dominated by what? By the number of so when you have to solve, for instance, a ridge regression or ordinary squares, the complexity of computing the solution is dominated by the samples. Of course, the samples are important because you grow, your complexity grows with the samples, but you have a cubic dependence not from the samples, but from the features. Because as you can remember, the matrix that needs to be inverted is a matrix that is number of parameters times number of parameters. And so, since in linear regression you have one parameter for each feature, so the number of features. So in the parametric world, in the linear case, your computational complexity is dominated by the number of features. The number of samples is less relevant. The idea of kernel methods is instead to change the complexity, and as we will see, the complexity will be no more the number of features or the number of parameters, because in the kernel method, as we will see, you have not explicitly parameters or features, because they are memory based. And the complexity is all in the number of samples. And so now someone can have some objection on this. So what we are doing with the kernel method is to move the complexity from the number of features to the number of samples. Is this good or not, in your opinion? Is it better to have a complexity that grows with the number of features or in the number of samples? Exactly. Usually samples are more than features. We have seen this with ordinary least square. We have seen that if you have more features than samples in ordinary least square, actually you cannot have a unique solution, because you have a matrix to be inverted that is not full rank, and so cannot be inverted. But we have also seen a ridge regression. In ridge regression, by adding the penalization on the LHC norm of the weights, you have seen that you are always able to have a solution, and this solution can be achieved even in the case where you have more features than samples. And so the idea of kernel method is that kernel method are very interesting to be considered when you'd like to work in a feature space that is much larger as for the dimensionality with respect to the number of samples. So suppose that you have 1,000 samples and you want to work in a feature space of 1 million of features. As you can imagine, doing this is very unpractical for a linear method, a parametric method, because you have, each time when you have a sample, you have to build the 1 million features. And this takes a lot of time, building so many features. And then once you have built all these features for all the samples in the training set, you have to compute the solution. And so you have a cubic complexity of something that has 1 million of parameters. And so actually it's impossible to be applied. But maybe you want to do this because you want to search in a very large feature space, because then you want maybe to regularize using, for instance, ridge regression. And so this is the case. Suppose that you want to do ridge regression with only 1,000 samples and 1 million features. The answer is you cannot do this. You cannot do this not because actually you cannot perform it theoretically. You cannot do this because practically you have not enough time for doing it, because it's too complex. And so in this case, you can use a kernel approach, as we will see. Because using kernel approach, you are able to build a dual problem that is equivalent to the problem that solves a ridge regression, but where the complexity of this new approach in the kernel world is not a function of the features, but is only, actually, the complexity depends only on the number of samples. So in this case, in the example, was only 1,000 and not 1 million. And this kind of magic transformation takes the name of kernel trick, that provides you this transformation almost for free. Of course, as you can imagine, if you are in the opposite situation where you have 1 million of samples and only 1,000 of features, it's not so reasonable to go in the kernel world, because, as we have said, in the kernel world is a memory-based approach, and so the complexity is dominated by the number of samples. So in that case, it's much better to remain in the parametric world. But if in this problem, if you have a problem where you want to use a very large hypothesis space, and so a very large feature space, and the number of samples is not too large, kernel methods are a very interesting solution. Okay. What about overfitting? As I've said, overfitting is managed using, in the example, using a regularization, as a ridge regression allows. You have the lambda parameter, and with the lambda parameter, you can avoid overfitting. But actually, if you have no idea of which are the good features, you would like to use many features and then apply regularization to discard the features, so to reduce the size of the hypothesis space with the lambda parameters. But the problem is that in some problems, you can need too much computational time to do this if you use ridge regression, because ridge regression doesn't scale so well with the number of parameters. And so you can use the kernel version of ridge regression in that case, if you want to do this. Okay, so lambda is used for managing the bias variance trade-off, but you want to start with a potential hypothesis space that is very large. And then you will do model selection. The good thing, and this is the very strong thing of kernel method, is that they are even able to work in a feature space with infinite features. That, of course, if you are in a parametric world, you cannot do, because you cannot compute the solution with infinite parameters. If you use the kernel method, you are able to compute in finite time even a solution that corresponds to a solution in a infinite dimensional feature space. It is a very strong result. Because we have seen that when you, of course, there is a lot of risk of overfitting, as you correctly have seen, but of course you need a method that is able to avoid the overfit. So you need some hyperparameter, like in ridge regression, that allows you to control the bias variance. Of course, you cannot do ordinary square in that case. You need to do something that has a way of regulating the variance. Okay. Another question. I didn't understand one thing. We have said that kernel methods are non-parametric methods, but now we are talking about a number of features. Because actually, as I told you, we will see that we can take, again, as an example, a ridge regression. We will see also another example that is the perceptron, and we can make many examples. We can take a parametric method, like a ridge regression, and by using the kernel trick, you can transform this method in a non-parametric method, but in a kernel method that is a memory-based method, that provides the same result. Okay, so the prediction will be the same because they are equivalent. But the difference is that in one case, when you are in ridge regression, you train your model, you have the parameters of your model, and then you discard the dataset and you use your model for doing the prediction. In the kernel method, instead, you use the memory. So you have to store the dataset always, and then you can use the dataset for doing the prediction. Of course, now I am anticipating a lot of things that we will see in the next slide. So, of course, now we will see how to do this transformation. But what I want you to understand before explaining how to do this is where we are going to arrive. We want to reach this solution. So we start from methods that can be done in the parametric world, and through the kernel trick, we transform them in memory-based approaches that are equivalent, but with very different computational complexities. Exactly, we will transform the more than the parameters, but the features. We will transform the features in the parametric world in kernel, in matrix, in the kernel world. This is what we are going to do exactly in a minute. And we will see that there is a mapping between these two worlds that makes them equivalent, but as I've told you, again, with very different computational properties. It's very powerful, it's very amazing, I think, this kind of transformation is something that has a strong impact and has produced a lot of very interesting and useful techniques. Okay, we have again the usual example that we have done before. So in this example, this is a one-dimensional example of classification where you have the points in this way. There is no linear boundary that is able in one dimension to split this dataset. But if we, instead of using only one dimension x, we use two dimensions. So we map each point in x and x squared. Now we have two features. And with these two features, of course, we are able to find a linear boundary. So now you see that the one-dimensional problem has been mapped in a two-dimensional problem, x and x squared. And now by plotting the points in this two-dimensional space, you can find a linear boundary that separates the green from the red samples. So this is what we have already done a lot of time in the parametric world when you simply add features. This is the solution that you use in the parametric world. This is another case. Now you have the points in two dimensions. Again, you are not able to separate, but you can find a new mapping by adding, for instance, in this case, instead of using the feature x1 and x2, you use the three features, x1 square, square root of 2, x1, x2, x2 square. So now you are in 3 dimensions, and if you write this in 3 dimensions, okay, you can find a plane that separates the blue crosses from the red dots. Or as we have already done another time, you can use the distance and the angle. You can use this for separating this kind of transformation for separating the points. So this is the way that was used in the parametric world, where you can change the features in order to make, hoping to make the points linearly separable. Of course, in this example was quite easy to design the features that achieve this result, but if I provide a huge data set with many input variables, understanding which are the features that are able to find this linear separation can be really challenging. And so this is the reason for which, when you are in this case, you want to project the data in a very high dimensional space, hoping that this projection separates the points. And of course, the more the dimension in which you project your data, the higher is the probability that actually these points actually can be linearly separated. And so this is the reason for which you may need a lot of features. But if you have too many features, you have a problem of computational complexity of using parametric techniques. For instance, suppose that you want to do this kind of feature mapping. So you start from data X that has M components, and then you want to do a feature mapping that starts from this M component and map to, for instance, in this case, all the second-order monomials. So how many second-order monomials do you have here? If you have M features, how many are the monomials that the mapping phi will produce? So you know that R, of course, the number of square terms is equal to M. And then you have all the combination of the pairs. Okay, they are in the order of M squared. Actually, they are M plus M times M minus 1 divided by 2. So in the order of M squared. Is okay? So this is the number of features that you will produce. And this is only by producing the second order monomials. And now suppose that I want also to have all the third order monomial, the fourth order monomial, the fifth order monomial, because I want to represent all the polynomial combination of features up to the fifth order. As you know, actually, if you want all these kind of combinations, the number of features grows exponentially, because they are all the combination, and this is a combinatorial problem. And so it means that even if you have a number of inputs m that is quite small, if I require you a monomial that is too high, they become millions, billions, very quickly. Okay? And so the problem is that, suppose that I require you the fifth order, you have 10 terms, so you do all 10 input variables, so m equal to 10, and then I ask you all these kind of polynomial features. The problem is that, okay, in that case, you will have billion of features that are required. And so then you have a problem, because, as I've told you, if you want to work in the parametric world, you should take each sample. Each sample needs to be expanded by computing all these features. And so starting from 10 input variables, you have to write, I don't know, suppose that is 1 billion of features. And so you take a lot of time to compute these features. You have to do this for each sample in the dataset. And once you have done this, you have to use all these features for computing the optimal parameters. As you can imagine, this cannot be applied. So the kernel idea will avoid to you to compute this expansion. So you will, when you use kernel method, even if you obtain a solution that is the same as you were using the features, you obtain the same solution without the need of computing the features. So the features will never be computed. They remain implicit in what? In what is called the kernel. And as we will see, in most of the cases, the computation of the kernel is very cheap, is much more efficient than computing the features. And we will see an example in a few slides. Okay, so this is the main point. The main point is that we will achieve the same result without the need of computing the features, because the features will be implicit in what is called the kernel. And now we will explain what is a kernel. First of all, a kernel is a function. In particular, is a function that takes as input two input data, x and x prime. Okay, sorry, they should be bold, x bold and x prime bold, as in the right hand of the equation. So you need to compute the kernel. And as you can see here, the kernel can be always defined as the scalar product of some feature expansion of the point x multiplied in the scalar product with the feature expansion of the point x prime. So again, x and x prime are two input points, and k specify the similarity, because the idea of the kernel function is that the kernel function specifies how much x is similar to x prime. And the way that is used to specify the similarity is the scalar product between the two vectors obtained by taking x and x prime and expanding them in some feature space using the phi function. For instance, a very simple kernel is the linear kernel. The linear kernel is the kernel that associated is associated to the identity function for the feature expansion. So phi is the identity function. It means that phi of x is equal to x. So actually you are remaining in the original input space. Suppose that phi of x is equal to x, and so phi of x prime is equal to x prime. So in the linear kernel case, you are simply saying that the similarity between x and x prime is the scalar product between x and x prime. So why this is a similarity measure? Because you know that the scalar product between two vectors is maximum when the vectors are pointing in the same direction, right? Because you know the scalar product between two vectors is given by what? Is given by the length of one vector times the length of the other vector multiplied by the cosine of the angle between the two vectors. This is the result of the scalar product between two vectors. So, since the kernel function tries to measure the similarity, when the two vectors point in the same direction, the angle is 0 and the cosine is 1, that is maximum, while when the two vectors are orthogonal, the angle is 90 degrees and the cosine is 0. So if x and x prime are orthogonal, actually they have a kernel that is equal to 0. If they point in the opposite direction, actually you have that the cosine is equal to -1. So when the kernel, there is a question. So when the kernel is the identity, we are performing cosine similarity. Nearly, because as you know, when you do cosine similarity, you have also to divide for the length of the vectors to have the cosine. While here, as you can see, is only the scalar product. So inside there is also the length of the vectors. So it's not exactly the same, but it's strongly correlated to the cosine similarity. If you use, let's say, if you use normalized kernels, that means taking this formula and divide the formula by the product of the length of the vectors, you have the cosine similarity. Okay, so this is in the case of the linear kernel. If you have another feature that is not the identity function, but you have another way of expanding the feature, like for instance the second order monomials, okay, this defines a new kernel. Okay, so one could say, okay, but what are you saying? You are saying that the kernel is the scalar product between two feature vectors. But you have said in the previous slide that actually in the kernel method, I never need to compute the features. Right, you're right. This is the definition. So you say that actually a kernel should always be represented, can always be represented by a scalar product between two feature vectors. The interesting thing is that you do not need to know which are these two feature vectors. It is enough that you know that your kernel function can be computed in this way. Even if you do not know phi, so the function that maps x to the feature vector, even if you do not know this value, you can use the kernel and solve the problem. We will see how to do this in a few slides. So first of all, we see some properties. So we see that the kernel, of course, is symmetric because, as we have said, if the scalar product is symmetric, and so also the kernel is a symmetric function. And as we have said, that the kernel can be interpreted as the similarity between x and x prime, is a kind of similarity between these two points. We have already said, okay, if we use the identity mapping, and so phi of x is equal to x, we have the linear kernel. For instance, when you use the linear kernel, it's just as you are working with a parametric method where you have the input variables as features. So where you are not using any transformation of the input variable. You are working in the original input space if you use this kind of kernel. So what is the idea of the kernel trick? The kernel trick is the following. If I'm able to rewrite my learning algorithm in a way in which the feature vectors always appear in scalar products, I can replace these scalar products with the value of the kernel function. So now what we will try to do, and we will do with some algorithm, is to take the parametric version of the algorithm and show that this parametric version can be rewritten by removing the features everywhere and replaces the feature with the value of the kernel. And so then we will use this kernel trick. As we will see, this trick can be used in with many algorithms. We will see only a few of them. We will see ridge regression, and we will see actually the perceptron that leads to the support vector machine. But this can also be applied for having a nonlinear version of the PCA that is called kernelized PCA. But we will see also this when we will see the Gaussian processes. We will see that the Gaussian processes are the kernel version of the Bayesian linear regression approach that we have seen. So there is a lot of connection between the parametric world and the kernel world. Okay, some definitions. So we say that a kernel is stationary if actually it depends only on the difference between the two points. So if the kernel between x and x prime is only a function of the difference between x and x prime. So if the property holds, this is called the stationary kernel. Furthermore, we call the homogeneous kernel a kernel that depends only on the distance, the Euclidean distance between x and x prime. So if is only a function of the Euclidean distance, we call homogeneous kernel. Pay also attention that, of course, when we talk about so x, the input of the kernel function is a vector of dimensionality m, but the kernel function is a scalar product, and so is a scalar. So is a scalar function. And as we have already said, for a kernel to be valid, valid is a very important term in a kernel. So we say that a kernel, so a similarity measure, is valid, so can be really used in kernel method, only if it exists a feature expansion phi that allows to rewrite your kernel as a scalar product. So what I'm saying is the following. Suppose that now you come to me and you say, professor, I have this kernel function here. And so you give me a function. And then I say, okay, not all the functions are valid kernel. If your function is a valid kernel, it means that should exist some feature expansion phi that you need to provide if you want to prove, or you need at least a way to prove that through this feature expansion, you can write your kernel function as a scalar product. Oh yes, there is a missing prime on the second x. Thanks for noting. I will change it. Okay, let me take a note. Thanks. Okay. So now we see how to do this, and so we talk about the dual representation. There is a question, the symmetric property is also necessary to be a kernel function, right? The symmetric property is implicit in the fact that the kernel needs to be a scalar product between two feature vectors, and since the scalar product is symmetric, the kernel function needs to be symmetric. Is a consequence. So, dual representation. Now we will see how we can move from a parametric method to a kernel method using the dual representation. And to do this, we will make an example using ridge regression. So we have already seen many times the loss function of the ridge regression approach. And so in the ridge regression approach, as usual, you have the first part of the loss function that is the one related to the loss in the prediction, so the sum of the square errors, and then you have the penalization. The penalization that is again lambda divided by 2, and then you have the L2 norm of the weights that, as you know, can be written as the scalar product of W with itself. That is the same as writing the L2 norm square of W. Okay, so this is the traditional loss function. So now, our goal now is to show that this loss function can be rewritten by making phi disappear. So we want to make phi disappear, and we want to replace phi with the kernel. In order to do this, we need to rewrite this loss function to make appear only scalar product of phi with itself in another point. So we need to find this kind of scalar products. In order to do this, we do the following transformation. So we take the gradient of this loss function with respect to W, and we put this gradient equal to 0. Okay. And here you see the result. If you take the gradient of W and you put equal to 0, you can find this solution. You find that W is equal to -1 divided by lambda, and then you have this summation. As you can notice, in this summation, there is still W. Okay? So this is quite strange, because it seems that you are defining W as a function W, so actually it's not really a definition. But as we will see, this actually will be useful to us. So again, you take the loss function of the ridge regression, you derive for W, and you put equal to 0. And then you rewrite this equation. So this equation simply is an equation that holds when the gradient is equal to 0. Now, we rename the term W transpose phi of xn minus Tn divided by -1 over lambda as An. So we introduce actually new variables. So in the loss function, the unknowns are W. W is our unknown, the parameter that we want to find. Now we change here, and we call the new unknowns that we want to have are no more W, but are An. An that can be mapped to -1 over lambda multiplied by W transpose phi of xn minus Tn. And so we have the summation from n from 1 to n, capital N, of An multiplied by phi xn. Actually, this summation can be rewritten as capital phi transpose multiplied by A, where capital phi transpose is what? Is again the usual design matrix. So capital phi is the matrix with number of rows equal to the number of samples and number of columns equal to the number of features. You make this transpose, so now you have number of rows equal to the number of features and a number of columns equal to the number of samples. And then you have A. A is a vector, and this vector is as a size number of samples. So the final result of this product will be a vector with a component equal to the number of features, because actually this is equal to W. Okay, so now what we are going to do is to replace phi transpose, capital Phi transpose A, in place of W. because we have done this kind of transformation here. Now, let's try to do this. So now I do this by hand. So I show you, then I show you also the final result, but I try to show you the passages. Do you see? Yes. Okay. So we have said we have the loss function. So the loss function of ridge regression. That we know that in matrix form, this can be written in this way. Capital phi W minus T transpose capital phi W minus T plus W transpose W. Okay, this is how we wrote the loss function of ridge regression in matrix notation. Now we want to replace W with the expression that we have found, that is capital P transpose A. And so what we get is phi, then I have phi transpose A minus T transpose, and here I have phi, and then I have phi transpose A minus T plus, and here now what I have, W transpose, you know, when you have a scalar, an inner product between two matrix transpose, you have to do, you have to swap the term and make the transpose. So W transpose is A transpose phi, and then we have phi transpose A. Is it okay? Okay. Okay, so now we simply do the product. Actually, you have that this term is transposed, so you have to rewrite it. So this is A transpose phi transpose phi. Okay, and then multiplied by phi transpose A. So this is the first product. Then you have minus T. Okay, sorry. Okay, then you have minus T transpose T divided by 2. Okay. And then finally you have minus A transpose phi transpose T. Actually, this term comes from the two terms. So this one is obtained by this product plus this product. So you have 1/2 ahead and so you sum and you have minus A transpose phi transpose T. Okay, so as you can notice here, in this final equation, you have that W has disappeared, because now we have A. And anytime that phi appears, actually you have phi transpose. Sorry? You say at T. Yes, you're right. Yes, you're right. Yes, this is in this way. Okay. Okay, so what we have said is that now we have all the time we have that anytime that capital phi appears, it then multiplied by phi transpose. And so this is actually what we were searching for. So we were searching to find the product of phi by itself. And why this is interesting, now we understand this by looking at this concept. Okay, so now we have the concept of gram matrix. What is the gram matrix of a problem? As you can see, it's actually a definition of the inner product between phi, capital Phi, and capital Phi transpose. So you know that the matrix phi is number of samples times number of features. If you multiply this matrix phi by its transpose, what you get is what is called a gram matrix. This is always true. Anytime that you have a matrix and you multiply this matrix by its transpose, the resulting is called a gram matrix. In particular, this is a gram matrix of the feature. And what is each single component of this n by n matrix? So it's a matrix number of samples times number of samples. If you look at each component of this matrix, actually each component of this matrix is the scalar product of the feature vector associated to the point n with the feature vector of the point m. This is actually the component nm of this matrix K. But for what we have said, the scalar product between two feature vectors is the way in which the kernel measures the similarity between the points, and so is the kernel value associated to the pair xn and xm. So the where is so sorry. Yep. Okay. So the gram matrix of the feature vector is actually a matrix of kernels. So you have the similarity of x1 with itself, x1 with x2, and so on until xn, and then so you have all the similarity between all the pairs of points that you have in the training set. So if you have 1000 samples for training, okay, you have a matrix that is 1000 times 1000 and specifies the similarity of each pair of points in your training set. This is the gram matrix, capital K. And the gram matrix capital K is equal to capital Phi inner product with capital Phi transpose. So now what we have to do is to simply take this matrix K and plug this matrix K in the loss function. So this is the loss function after the replacement that we have done previously. And now if you replace capital Phi times capital Phi transpose with K, you have this new loss function. And if you look at this loss function, this loss function is no more a function of W, it's a function of A. So now the unknown is A. And as you can see, the feature here have disappeared. You have only similarity measure, only kernel measure, K. Okay, but this is exactly the same, if you want, is the same loss function as before, but that is simply now rewritten not more in terms of features, but in terms of kernels. Okay, and now if you want to compute the solution of this new loss function, so you want to find the A that minimizes this loss function, you compute the gradient of this loss function here. And once you have computed the gradient of this loss function, you put the gradient equal to 0. This is, again, as you can see, is a quadratic function of A. It can be proved again that this loss function is convex. And so there is only one optimum, global optimum, that can be obtained by the following formula. So A is equal to the Gram matrix K plus lambda, the identity matrix of size n, all inverted, multiplied by the target vector T. If you look at this formula, you will see that actually is quite similar to the formula that we had for the ridge regression case. If you remember, in the ridge regression case, what we had was W is equal to, and then we had phi, capital Phi transpose phi plus lambda, identity of M, not N, because if you remember, the size of the matrix that was inverted in the ridge regression case was M times M, so number of parameters times number of parameters. While in this case, the matrix that we are going to invert is not, of course, a function of the number of parameters. Why? Because the parameters in the kernel method do not exist. You have no features in the kernel method. And so it's only a function of the number of samples and how much these samples are similar. So now the matrix to be inverted is N times N, no more M times M. And then you have the product with T, that in the case of the parametric version, there was capital Phi times T, because of course, in that case, you have to move from the samples word to the feature word, and so you need the multiplication for the design matrix. While in this case, the number of elements A is equal to the number of samples. So A is a vector with number of sample components. K is a matrix, number of samples times number of samples. Lambda in, lambda is a scalar, in is a matrix, number of samples times numbers of samples, and T is a vector, number of samples. All these components have a dimension that is a function of number of samples. Is it a surprise? No, because we have said that in a kernel method, the number of features doesn't exist because we have no features in a kernel method. But we have only samples. And once you have computed the optimal value of A, now you can compute the prediction. How? In this way. You know that if you were in a parametric method, the prediction is the optimal parameter W multiplied by the feature vector. This is how the optimal solution is computed in the parametric world. But we have said that we do not want to have this anymore. We note that W is equal to A capital Phi transposed. So by applying the transpose, we have A transpose phi that multiplies phi of x, but we have the product of capital Phi by phi that produce the vector k of x. What is the vector k of x? The vector k of x is a vector of n components that measure the similarity using the kernel of each sample in the training set with respect to the sample x that is the input for which we want the prediction. So again, the model that predicts the value for new samples is done in this way. So we get a query point x, and in order to predict the solution, what we do is simply multiplying the similarity of each point in the training set with respect to the query point, and this is the vector k of x, multiplied by the vector a. The vector a that is equal to the matrix k plus lambda I of n minus 1 transpose. And so, as you can see, you are doing the prediction by simply averaging the values that you have in the training set for the target vector t using weights that are related to the similarity between the samples. And the final result will be the same as working with a linear model in the feature space represented by phi, simply by never computing phi, but only k. The cool thing is that k can be computed even if you do not know what are the features phi that represent the kernel k. There is a question, so the vector k will have at least one element equal to 0. No, why? Why this? Sorry. So the vector k is the similarity between, so why 0? No, I cannot understand your observation. So you have a query point, a new point, where you want to do the prediction. And then you compute the similarity between this point and all the training samples. You will have different similarities, but you have no guarantee there is 0. Because if you compute a vector between one point and the other, there will be the scalar product between the point and itself. First of all, the scalar point between a point and itself is not 0, but is maximum, because it's maximum similarity. The scalar product between a point and itself is equal to the L2 square norm of the point. But when you are doing this, x is a new point, is a point where you have to do a prediction, is a point that you have never seen before. So it's not present in the training set. And so there is no this product of x with itself. Because you have a training set, and now you have a prediction that you have to do on a new point that is not the same as the point that you have seen before. Of course, it can happen that you have to predict something that you have already seen, but in the general case, you have never seen that point. Yes, the endpoints are the points in the training set. The prediction is this one. No, you do not need to compute phi of x for every x. You need to compute k of x prime for each pair of points. And as we will see, computing k does not require to compute phi in some cases. Now I think that is just in a few slides this. Okay, so what we have done so far is taking a ridge regression, that is a parametric method, and transforming it in a kernel method that works implicitly in a feature space that is never computed, but that is implicitly in the choice of the kernel function that you have done. So what is the advantage of this? The advantage of using a kernel function instead of the features, as we have said, is that if you have a kernel function, very simple kernel function, that corresponds to a scalar product of feature vector with many, many components, you save a lot of time. As we will see, there are very simple kernel functions that can be computed in no time that correspond to feature vector with infinite components. And so the gain is infinite in terms of time in that case. So while this is the solution that we had for the ordinary square, if you sum lambda I, you have the solution of the ridge regression. And so we had that the cost was the one of inverting this matrix that is m by m. So now we have to invert a matrix that is n by n. And as we have said, this seems not to be a real advantage because usually we are used to work with a number of features that is smaller than the number of samples. But the cool thing of kernel method is that they allow you to work in a different setting where you have many more features than the number of samples. If you want, the real drawback of kernel method is that they do not scale well with too many samples. The problem is that you are able to use kernel method if you have training set with 1,000, with 10,000 of samples. But if you have millions of samples, of course you have problem because you are memory based, and so your computational complexity scales with the number of samples, and so you are not efficient in that case. In that case, it's better to use, if you have many samples, it's better to use parametric method with respect to kernel method. But if you have a few thousands, 10,000 of samples, kernel method have this real advantage that they are able to work in very complex feature space with a very low computational cost. The other advantage of kernel method with respect to parametric method is that the kernel function, as we will see, can also be defined not only over numbers, but can be also defined over objects. And so, because actually it needs to represent the similarity between objects, also over symbols. And so you can represent this concept of similarities. And so this allows to apply supervised learning techniques even on the dataset that is not made by numbers, but made by conceptual objects or something like that. So this is quite interesting. Okay, let's see at the core. Probably the question that you have in your mind and say, but you have said that the kernel is a scalar product of features, and so how you are saying that you are not using the features because the kernel is a scalar product of features? Now I will show you that you can use kernels even if you do not really know which is the feature vector that is behind them. You are sure that exists, but you do not know which is. There's a question. This is because we simply have to define the metric. Yes, yes, because you simply define the metric. Of course, you need to be sure that the metric is valid. This is the problem, because not any function is a valid metric. But if you are sure that your function is a metric, even if you are not able to decompose in a scalar product of feature vectors, you can use it. So the goal is that we need a valid kernel function. There are many different approaches. So the first approach is the trivial one, in the sense that you know the feature space in which you want to work. And so you have decided that you know it. And so now you simply do the scalar product of the feature vectors. And so you obtain the kernel. Of course, this is the less interesting way of building the kernels because, again, pass it through the concept of feature vectors. Okay, let's skip this. Let's see the example. The second method. The second method is the one that is interesting because the previous one, as we said, is not interesting because actually to compute the kernel, you have to compute the scalar product between features. But this is useless because in this way, if you are able to compute the features, you use a parametric method. This other one is by trying to directly construct your kernels. For instance, suppose that you have this kernel function here. So you decide that you want to use scalar product between the input points raised square. And then you ask yourself, is this kernel a valid kernel, yes or no? So to prove that this kernel is a valid kernel, you should find a feature expansion that is able to provide this result. For instance, in this case, this is possible, because if you look at the second line, you see that if you use x1 square, square root of 2x1, x2 square, and the same for z, so this kind of feature expansion, and you do the scalar product between these two feature vector, actually you obtain the scalar product of x and z raised square. So this means that the kernel scalar product of x and z raised square is a valid kernel because you have found a feature expansion that obtains this result. But pay attention, you do not need to compute, when you have to compute the solution with the kernel method, you do not need to use the feature expansion. It is enough to use the kernel function. It's the same, and not really, because for computing the feature expansion, what you have to do? You have to, first of all, to compute x1 square. You have to compute square root of 2x1, x2. You have to compute x2 square, and then the same for the other one. And then you have to do the scalar product that involves the multiplication and the summation. While if you want to compute the kernel directly, you have to simply compute the scalar product between x and z. That is 3 multiplication and 2 summation. And then you have to do the square, so a product. So they are less operation than in this case. And here, of course, is a simple example, and the saving is small. But if you imagine now to generalize this concept a little bit more, you have the following. Suppose that you want to do this. So consider this kernel. That is x transpose z plus c is a scalar value, a constant, raised square. We can prove that this kernel is again a valid kernel and correspond to what? Correspond to all the monomial between the zero, from the 0 to the second term. So you have all the 0-order monomial, that is 1, the constant. You have all the 1-order monomials and all the second-order monomial. And this is true for all, of course, independent from the size of x and z. And as we have seen, computing all the 0-order, 1-order, and second-order monomial, if you have many values in x, grows quadratically with the size of the vector x. While computing this term here, okay, is still linear in x. And even more, if you take the kernel in this way, so you take x transpose z plus c, and you raise at any power p, you get all the monomials up to the order p. And you know that actually here you have an exponential growth of the number of monomials as p increases. And here, the cost is always linear. So you are able to build a kernel that is equivalent to a number of features that is a billion, even by only computing this simple kernel function here. It's a lot of saving. So if x has 10 components and p is 100, even 10, you have no hope of computing the feature expansion. While with the kernel function, you have no problem. You have to do a scalar product between two vectors of size 10, that is fast, sum a constant, and raise to the power of 10. Very cheap. Of course, you have to do this for each pair of samples. So you have to compute this function n squared time. So it's clear how much is powerful or not. So once you use this kernel, this one, you are able to work in this very large feature space without the need of computing the features and solving and computing the value of the parameter associated to these features. Is all the complexity is actually implied by the number of samples. In this case, the role of the constant C is to generate all the monomials. Because otherwise, as you can see above, if you do not put the constant C, you have only the second order monomials. It is enough to add the C to have all the monomials from the second order up to the zero order. The same happens for the P case. Okay, so we choose a kernel with a lot of features, and we are hoping that some of the features are useful. Is it a good way to select the relevant features? No. So the first part is okay. So the first part of your question is okay in the sense that exactly you are using this kernel because this kernel implies to work in a very large feature space, and so you hope that in this very large feature space you will be able then to find a solution. Pay attention that you are not working in the feature space, you are working in the sample space, so the feature will never appear. You are not selecting features, you are directly predicting the result by combining your training set like in a memory-based approach, like in KNN. You take the sample, you average the prediction by giving different weights that are somehow related to the features, but the features are implicit, they will be never explicitly used. And you do not need them. You do not need the features because you have already the prediction, and the prediction is computed without the need of the features, but only by computing the kernel. Is this clear? Okay. Okay. Another way of understanding if a kernel function is a valid kernel is to use this necessary and sufficient condition. So a kernel function, a function is a valid kernel if the gram matrix, so K, that is composed over this kernel function for any choice of input points needs to be positive semi-definite. So what does this mean? It means that actually the kernel to be valid needs to represent a function that is positive semi-definite in the sense that induce a kernel function, a kernel matrix that is positive semi-definite. Positive semi-definite means that is a matrix with all eigenvalues that are non-negative. You know, the kernel matrix K is a symmetric matrix because you know that the kernel product is symmetric. Sorry, the scalar product is symmetric, and so this function is symmetric. So what we need to have is that this function produces a positive semi-definite gram matrix K. In other way, anytime that you take any input vector x and you multiply x transpose kx, the result should be greater than or equal to 0. So this leads to this theorem that says that for any, if you have a kernel function that is continuous, symmetric, and positive semi-definite, where positive semi-definite is what we have written here above, can be always expressed as a dot product of some feature space. And so it means that you have a valid kernel. So necessary and sufficient condition for having a valid kernel is to have a function that is continuous, symmetric, positive, semi-definite. If you are in this case, okay, this is a kernel. Do you need to have the features? No, it's not important that you find this feature. You have this theorem that guarantees that this feature exists. The shape of this feature, who knows? But it's not important. It's much more important that when you build a kernel, the most important thing is that you think if the function that you are writing really represents a similarity between your samples. because the meaning of the kernel function is that these two samples are similar. So, of course, the kernel needs to be valid, otherwise you cannot apply the approaches that we have seen. But among all the valid kernels, the kernel that you would like to find is the kernel that really expresses when two samples are similar and when not. So kernel method, of course, do not solve any problem, because in the parametric case, the problem was finding the features. As you can imagine, in the kernel world, the problem will be finding a good kernel. Good features, good kernel. If you have no clue about which are the good features, maybe you are better in thinking what is a good kernel. Maybe is the case. Because maybe for you it's easier to reason about similarity between samples with respect to thinking about what are the features that are useful for predicting the target. It's a different perspective on the same problem, but it's a different perspective that has different properties. It's not always said that kernel methods are better than parametric methods. It depends on the application and on how much you are easy to parameterize and to choose the features or the kernels. Another way for building kernels that is very interesting is by combining existing kernels using some functions that are allowed. And these are the functions. For instance, you have a set of operations that preserve the validity of a kernel. So suppose that you have some kernels that are valid. So you start with kernels that you know that are valid because you have proved in another way. Once you have this kernel valid, you can combine them in many different ways, and you can still preserve validity. For instance, if you have a kernel, you multiply a kernel for a constant, of course, you are not changing the validity of the kernel. The same is, for instance, if you apply any polynomial transformation to the kernel, you have a gain. If you apply the exponential function to the kernel, it's the same. The sum of two valid kernels is still a valid kernel. The product of two valid kernels is still a valid kernel, and so on. So there are all these kind of transformation that, starting from kernels that are valid, produce kernels that are still valid. And so you can build new kernels using this concept here. For instance, we can prove, using this technique, that the commonly used Gaussian kernel, this is is very commonly used, this kind of kernel. And as you can see, this is an homogeneous kernel because it depends only on the Euclidean distance between the point. As you can see that you have the norm of the difference between the points, so it's an homogeneous kernel. And as you can see, is a negative exponential of the distance, the Euclidean distance between the 2 points at square, divided by 2 sigma squared, that is called the bandwidth of the kernel, so how much the Gaussian is wide or not. So you are saying, using this kind of kernel, you're saying that 2 points are similar if they are close. And you say that as long as their distance grows, their similarity reduces. We know that in this case, you have that when the points are the same, so x is equal to x prime, you have that the kernel is equal to 1. And you know that as x and x prime gets apart and get far away, you know that the kernel goes to 0. And so it's a typical similarity measure. How we can prove that this kernel is valid? We can prove this by starting from, by doing some kind of decomposition and proving that it holds. For instance, we know that actually the L2 norm square of the difference between x and x prime can be rewritten in this way. So as the sum of this scalar product. So x transpose x plus x prime transpose x prime minus 2 times x transpose x prime. You see what? Each one of these is a scalar product of a linear feature. So this is the linear kernel. And we know that the linear kernel is valid. So now the sum of the product of a linear kernel by a constant is still valid. the sum of a valid kernel is still a valid kernel. And then we know that also the exponential of a valid kernel is a valid kernel. By applying all these things here, we can prove that we can start from a linear kernel, and we can prove that we can achieve the Gaussian kernel. We know how to, so since we have used this approach now, once you know that the Gaussian kernel is a valid kernel, it means that exists some feature vector that represent the Gaussian kernel. In this case, you have arrived here, and you have never used this feature expansion, but you are sure that exists because you have followed the properties. So the Gaussian kernel, for sure, is associated to some feature expansion. And you can use this even if you do not even if you do not know this feature expansion. And this is actually is a good thing, because if you want to compute the feature expansion associated to the Gaussian kernel, you will find that you need infinite features. And this is the case that I was referring before. Computing the Gaussian kernel is quite cheap. You do not take so much time in computing the Gaussian kernel. But if you would like to use the parametric method associated to the Gaussian kernel, the associated parametric method needs infinite parameters because needs infinite features. And of course, cannot be performed. So the interesting thing is that using kernel method, you are even able to work in a feature space with infinite dimension. And the simplest case in which this happens is the case when you use as a similarity matrix the Gaussian kernel. Do you have questions? I say that we have run out of time, so we say that we can stop here. So if you have questions. It's not clear what you mean with parametric kernel. Actually, so better. If you look at the Gaussian kernel, for instance, the Gaussian kernel has a parameter. A parameter is a sigma square. So sigma square is a parameter of the kernel. And of course, you can do also cross-validation for finding the best value of sigma square. This is commonly done. So usually, kernel has a few parameters that are hyperparameters of your problem. Changing the parameter of the kernel means changing, if you want, the feature space. And so it's the same that you do in parametric method when you change the number of features. In the kernel world, what you do is changing the parameter of the kernel, or you can also change the kernel. Other questions? Is it ever useful to go back to the feature space after having found in a good kernel? It depends on what you have to do. Usually it's not done, because if you are able to go in the feature space, probably you will go there. Maybe you want to do this for having more interpretability, but it's not commonly done. Suppose I already found a fix where my problem is linear. How can I search a kernel to improve performance? It's not really clear, this question, because if you have already found a feature space where your problem is linear, okay, you can use simply that feature. You can build the kernel by doing the scalar product of that feature space, and you can work, if you want to work in the kernel space, because you have or better, if you are able to find a kernel function that contains that feature space, but that can be computed much faster than computing the feature itself, it's better to go in the kernel world. Otherwise, if you only know the feature expansion, is not that useful. So for explaining better, suppose that you are in this case here. In this case here. So suppose that you know that these three features are good. And you discover that by doing the scalar product of the feature by the other feature, you can find a more convenient way of computing this scalar product, that is the value that you find above for the kernel. In this case, you have an advantage in doing the kernel world because if you have not too many samples, because of course you have a more efficient way of computing the feature space using the kernel. It's not clear what you mean when you say to improve performance, because if it's already linear in that case, so your performance is already good. Okay, well, yes, if phi of x has many features, you have to try to see if writing the kernel function can save time by seeing if you are able to write it compactly. You have to try to see if you can synthesize the scalar product, as in the example or in many other examples. Other questions? Okay, so we can stop here. Okay, bye-bye.